Okay, I think that's about all the participants have come in. Okay, we will start the session. So good evening, participants, and a very warm welcome to another session of CIC's webinar series. It is a pleasure and honor to welcome Mr. Dev Anand, who is the Managing Director and Chairman of Kankyo Group of Companies. A very brief profile about Sir. So, hello, Sir. So, Sir, Mr. Devanand, the Chairman and Managing Director of Kankyo Group of Companies, he is a mechanical engineer with a master's in environment management and business administration with over 3 decades of experience in the field of renewable energy, water and wastewater treatment, solid waste management, and thermal engineering. He is the alumni of the prestigious IVLP program of US on climate change, clean energy. He is a consultant panelist of Waste to Energy for World Bank US, and he has a vast collection of indigenous research work to his name and has an immense experience in the area of sustainable engineering and technology. It's an honor to have you here, sir.
Yeah.
Okay, and before we start, a very brief introduction about CIIC. So Crescent Innovation and Incubation Council is an incubator based out of Crescent University, Chennai. So what we exactly focus is on our thrust areas are life sciences and industry 4.0. Currently, we have around 64 startups incubated with us. And what we exactly offer are the three M's, that is money, that is we identify the different grants provided by the government and from private investors such as angel investors and venture capitalists. And the second is mentors. We identify the requirements of the startups and provide them to different mentors who are experts in their particular fields of requirement. And thirdly, we offer the markets, that is the marketplace, identify the different marketplace where they can market their product or enable startups to find a marketplace. So that is what CIIC does to all these startups. And CIC has also bagged the fourth best bio incubator in India. So that is a cap on CIIC. And next to the participants, if you do have any questions, please do post your questions on the chat box. We will have the Q&A session towards the end. And also, if you want to have a one-on-one session with Dave sir, you can always click on the raise hand option so that we can unmute you so that you can talk to sir directly. Yes, that's about it. Over to you, sir. Thank you.
Oh, thanks, Alicia. So thanks for that introduction about me as well as CIIC. So, and thanks all participant to take your time, and you have joined on a Sunday. So welcome all. Good morning for the participants from abroad, and good afternoon for the local participants. So it's nice to see the participants are getting registered and just getting online now. So today this topic is I'm going to talk about the smart wastewater solutions. I want to just keep it very simple. I don't want to go into too much of technical stuff, but at the same time give some basic information about certain technologies and technological approaches which we can implement in our projects. And so my focus would be mainly on that. So I would just run through the presentation. So at the end of the presentation, we can have a Q&A session. So in between, if you have any queries or something like that, you can just post it in your Q&A box, and we shall also reply. And I'll also share my email address. So where specifically, if you have any queries, you can also mail me. So later on, I'll get in touch with you directly. So the topic what I would be discussing in detail would be about smart wastewater management. And before that, I would just like to give a small introduction about our organization, Kankyo. So, and Kankyo group of companies. So, Kankyo mainly focuses on these five verticals. Water and wastewater treatment is one of the vertical where we focus on industrial as well as domestic wastewater, and bioremediation on the water body remediation, soil remediation. So this is one of the other core area, and solid waste management. So we focus on industrial hazardous waste and non-hazardous waste, and garbage as well. And under waste to energy, we focus on converting waste into resource. It could be an energy or an useful other resource. So we convert it into a useful resource. Then air pollution control. So industrial air pollution control for controlling the emissions, NOx, SOx emissions, and particulate pollution, and as well indoor air pollution control like volatile organic compounds, and as well the bacterial levels, particulate matters. So all these things we have a solution for indoor air pollution control as well. So these are the five verticals where we work on, and we do the complete turnkey assignments, right from design and engineering, and doing the value addition by deploying the right technology, the complete project execution and operation and maintenance. So the complete spectrum of scope is covered for each and every project. No, that's a brief intro about our organization. So today my core focus would be on a few areas. So I would be running through a little bit of basics on the wastewater microbiology, because we are going to talk about smart solutions. So we need to understand basically how the microbiology works in the wastewater treatment, and how effectively we can harness for different streams of wastewater. And the other focus mainly when we talk about smart is always connected to sustainability. So it's energy optimization. So energy optimization, how we could optimize on the energy on the total treatment. So we'll be talking about those aspects and approaches, and also talking about some of the technologies which you must be already aware of. Certain technologies must be new to you, and so we'll be talking about these technology approaches for different wastewater streams. Then we have the smart monitoring and control of all these systems, which are the essential controls or monitoring, remote monitoring, which are essential for running this plant efficiently. So I would be slowly going through this steps, starting from wastewater microbiology, then going into energy optimization, technology introduction, and smart monitoring and control. Now, when it comes to the any wastewater treatment plants, or let it be for a domestic sewage treatment systems, or industrial wastewater. So these are the key design issues what we find normally. So one is that sometimes the systems are over designed, anticipating that a lot of factor of safety, and so the systems are over designed, and then in reality it is underutilized. So you spend a lot of energy onto it, or the system may not also perform when you're operating at a lower load, because the biological system need an organic load. So this could be one of the issues, and in many of the treatment plants, that's what we see, that design capacity is high. Always we can have a factor of safety to some extent, but when it goes beyond a certain limit, so we call that as an over design. And at the same time, on the contrary, we have under designed plants also. So mainly most of the places we have seen that the sizing of the system is very narrow. It will be a touch and go situation, or it will be under design totally, and it cannot handle the pollutants load, and then it becomes a total shutdown. So this is what we have been seeing in the industry as well as the domestic sewage treatment systems. Then the other approach, what we find is that OPEX driven. So I find that people don't normally focus on the capex part of it. So they want to keep the capex as low as possible. And but in many of the technologies which has a very low capex has a high operational expenses. So in the long run, if you see that, the expenditure and the hidden costs associated with that are pretty high. At one point of time, they don't even operate the plant. This is what the scenario we have seen, particularly in a, to give you an example, in a typical township, like where you have let's say you have a sewage treatment system in a township. So that is one of the area where a lot of energy is being consumed. So they just go and switch it off all the treatment plants, feeling that, that they should, they can save energy, but it's not so, so it has all other problems associated with that. So, and operators also, they don't have proper operators to operate these type of plants. So most of the plants are installed based on the capex. If it's a low capex, yes, I can invest so much, so I can just adopt this technology. But it has a lot of other operational expenses later on, which is not being could not be handled by the end user. Then also we are seeing that there is a replication of technology, that is blindly following the technology, for each and every effluent. Even for that effluent, we need to customize certain things to fine tune to that particular requirements. So otherwise it becomes very difficult. Many of them, they don't even share the wastewater quality reports, or they say it's an industrial effluent, so whatever you are given to my neighbor, give the same thing, and this is the BOD and COD. So so those BOD and COD are not only the deciding parameter. We should also know what is contributing to that BOD and what is contributing to the COD, so that we can effectively give a very, very effective solution. So just copying the technology what others are following will not, in the long run, will not benefit the end users. So this is one of the other issues what we find. And the other one is on the operational challenges. The operational challenges is the what parameters to monitor. What are the critical parameters you have to monitor on a periodic basis? And many of them, they don't even maintain a logbook. The logbook just gives only the physical parameters of it. Even we go for a master health checkup every at least once in a year or once in 6 months, to ensure that everything is working well. So when the wastewater is also like us, it's a living organism. So we should know the health condition of that particular system, whether it is operating well or it is approaching some difficulties. Only when the system is under breakdown, we evaluate all those things, and again we restart, and we lose a lot of time during this phase. And we don't have the proper record of all this information. So it becomes difficult for the solution provider also to analyze this actual problem. So a lot of time is lost in resetting the entire plant. So these are some of the issues what we are facing currently as well. And there is a life cycle approach. This is also not there because, as I told you, people want to go for a very low capex system. So whichever is cheaper, and so quality comes secondary. So most of the systems, they just go, they have to replace it frequently. And within a year, they would have replaced many of the spare parts or the components several times. At one point of time, we see that they don't even operate. They get fed up with the treatment systems and say that the system will not work. So in this journey, we have one person will be the designer, one person will be the developer, and one person will be the end user. So in this scenario, each one will have a different mindsets. And at the end of the day, if you see the end user is getting badly affected, the purpose is not solved. So these are the key design issues. So where we find this quite frequently in the market. Now, our approach, we have to focus on all these things when we are evaluating our wastewater treatment systems is very, very important, and take each and every wastewater as a customized solution. You may have a prefabricated solution, but you have to fine tune or customize it to that particular requirement, trying to understand more about what is contributing to this BOD and COD and whatever it is, So that is very, very vital in ensuring that we provide a sustainable treatment. Now, smart approach. So the what is meant by smart? Smart is being smart in our approach and having a smart system. So this is the smart approach. So there are two main core areas where we have to focus. One is on the selection of the process. The process selection is very, very, very important. Okay, and the other one is on the process control. So the selection and control go hand in hand. So together we call this as a smart approach. The entire goal will be to have lesser operational expenses. So reduce on your energy consumption. So energy optimization is one of the core forte, and reducing the overall carbon footprint of that wastewater treatment system, and ensure a consistent performance and achieve a sustainable treatment. So this is the smart approach what we have to focus on. Now, coming back to the understanding of the wastewater, so the wastewater anatomy. So it has a different components into it. If you take a wastewater treatment system, it has a lot of mechanical stuff into it, and civil components would be there in the form of tanks and foundations and all those things. And electrical is involved, instrumentation is involved, chemistry, biotechnology. So all these things, it almost covers all engineering in, so on the wastewater treatment. So each one is dependent. If the mechanical system is not proper, it will affect the process. If the electrical system is not working properly, the process gets affected. If the instrumentation is not there properly, you cannot monitor the system. So it's all these things are interrelated, which are very much essential for any of the wastewater treatment systems to perform well. Now, coming back to the families of the microorganisms, there are a variety of microorganisms in the wastewater application. So let us not go into the deeply on what are the different types of microorganisms, but we'll just see on the overall thing, like, what are all the things which are available. So broad classification is we call aerobic microorganisms, which are quite common. So which needs oxygen, and the pollutant is consumed as the food. So, and some nutrients. And with this, the end product would be stable solids and carbon dioxide and water. So this would be the end product. So this is basically called aerobic process. So the microorganisms thrive on an aerobic environment. Now, anaerobic is quite contrary to that, where there is no supply of oxygen into the system. This is entirely in the absence of oxygen. So the microbes convert this food into methane and some solids and carbon dioxide. This will be the end product for any anaerobic treatment systems. So if you see in aerobic and anaerobic, basically the anaerobic systems are pretty slower to stabilize, and aerobic process will be very faster in stabilization. So when we are adopting these two technologies for a wastewater treatment plant, so we have to see the limitations as well as anaerobic and aerobic, because anaerobic is a very, very sensitive microorganisms, because if something goes wrong, the plant stabilization time takes a very longer time. So we have to properly evaluate the usage of anaerobic treatment systems. And the same time is even for the aerobic process. And facultative microorganisms is again, which can survive in both the environments, in the aerobic as well as anaerobic environment. It can survive. So basically it needs food and nitrates and nutrient, and finally it gets converted into carbon dioxide and nitrogen gas. and some stable solids. So these are facultative types of microorganisms. If you see the bacterium process, you see there are 3 steps involved. It's the carbon intake and ingestion, because the basic molecule is carbon. So that is what is the basic energy which is consumed by the microorganisms. And this is again used for 2 processes, what we call it as a catabolic activity. So the catabolic activity is breaking of this carbon chains and converting that into a final product as CO2. Okay, so and for which oxygen is also required. So this path is what we call it as catabolic path. And then the energy which is generated in this process is again utilized for the growth of new biomass. So that process is called, we call that a cell synthesis. That's called anabolic activity. So it gives out a lot of heat as well. So this catabolic and anabolic activity together is what we call it as metabolic activity. So when you say metabolic activity, these 2 functions has to perform well. Then we can say that it's a balanced metabolic activity. Now, as far as the treatment is concerned, then anaerobic or aerobic is always, you can see that the aerobic is, this gives a typical example where a lot of energy input is required in the form of oxygen for the aerobic microorganisms to survive. And a lot of biomass is produced. If you see, it's around 100 kgs of COD, so it gives about 30 to 60% based on the nature of the wastewater. And rest, there is a carbon dioxide is there, and a lot of heat. It's an exothermic reaction, so we have a lot of heat loss as well. And but there will be an overall very good reduction of the organic pollutants, like COD from 100 kgs, you can bring it down to 2 to 10 kgs of COD. So that's a major advantage. And as far as the anaerobic systems are concerned, from 100 we can bring it down to around 15 kgs. The sludge generation is lesser. We don't require any external energy in the form of oxygen, because this happens in the absence of oxygen. And it gives out a lot of energy in the form of biogas. So that is biogas is a fuel, so which can be used for any thermal application or for power generation. So we have to find out in certain wastewater treatment streams where we have to go with the hybrid solutions if the organic load is heavy. So assume that you have a very high organic load. So if you're going only for the aerobic system, yes, it works. We need to work on a multiple stages of aerobic systems, but the energy consumption would be very, very high, so which will be uneconomical. So usually when the organic load is very high, so usually you'll start with an anaerobic microorganisms, because the anaerobic microorganisms are pretty hungry microorganisms. They need a lot of organic load to survive. So if there is a high COD, BOD effluent is there, so it's always better to go with these anaerobic systems to start with, which can reduce to the tune of about 60 to 70% of the organic load. Then the balance of the 30% can be taken care by the aerobic process. Because only with the anaerobic system, you cannot achieve the discharge standards. Okay, so we need to have a combination of anaerobic followed by an aerobics. There is always a limitation for an anaerobic system. But together it reduces on your energy consumption, as well as the generation of the sludge can be drastically reduced. So we are just running through the different classification of microorganisms what are present, where a lot of energy is being spent. So we need energy to break the bond. So in some of the process, as a byproduct, you get energy. Some process they consume the energy. So whatever input energy you're giving is getting converted into a different forms of energy. Now the other process is so far the aerobic and anaerobic treatment process, whatever the microorganisms what we saw, is basically to reduce the BOD and COD, biochemical oxygen demand, and as well as the chemical oxygen demand. So now the other parameters would be like there will be a lot of ammonical nitrogen in the wastewater, because these ammonical nitrogen, if it is not during the aeration process, gets converted into nitrates. Then it produces a nitrate pollution, so nitrates get into the soil and creates a lot of, it comes in contact with the groundwater. It creates a lot of other problems. So basically we need to remove the nitrates. So we have to go with the process called nitrification and denitrification. These are two different families of microorganisms. So in the nitrification, there are two different types of microorganisms which work predominantly, are nitrosomonas and nitrobacter, which converts the ammonia into nitrate and then to nitrate. This process is what we call it as nitrification. This is again an aerobic process. So after that, it will be your denitrification process. The denitrification process will further convert these nitrates into nitrogen. And in this route also, it will have other byproducts as well. So, and this is let out in the atmosphere. Now, these two systems combined, and the nitrification and denitrification, both combined together can convert all the ammonical nitrogen into nitrogen, so that there will not be any nitrate pollution getting into the water bodies or groundwater. Now, all this forms the part of the treatment. So because the regulation says that now you have to reduce the total nitrogen as well as the ammonical nitrogen. So in many of the countries abroad, this is a very, very essential system. But in India, usually they don't follow any nitrification and denitrification. Only off late, the norms have been revised, and we have to cut down on your total nitrogen and ammonical nitrogen. So now many of the plants we have to do a retrofittation. So now what is happening is that in the existing, nitrification also requires oxygen for its survival. All these microorganisms, they take oxygen. Now, whatever oxygen you put in a aeration system, the first will be the carbonaceous conversion into CO2. That's what happens. So it will not undergo any nitrification immediately. Only after the BOD conversion is happening, so breaking of all this organic pollutants into CO2, then only this nitrification process happens. So we need to give some excess air into it, and excess energy consumption would be there for this. So we call it as BOD removal and nitrification. Put together, it requires more oxygen than only BOD. Because some people, they give a treatment system without nitrification because their blower capacity will be very less. If you see it's nitrification also is included, then the blower capacity will be very high. So this we have to ensure, because the new guideline says that we have to reduce the total nitrogen content. There is another important one, is a biological phosphorus removal, mainly the phosphorus or the phosphate, which is present in the wastewater. Now you might have seen that many of this sewage, whatever is being treated, is being let out in the water bodies. And you see a lot of algae formation is there. And these are all mainly because of this eutrophication, because of high phosphate content. This phosphate content mainly comes from the surfactants, what we use, mainly from the detergents, soaps. So on a day-to-day, everyday life, you use these detergents in vast quantities, and these get into the water bodies, because currently none of the treatment systems have a phosphorus removal in India. And so this has become very, very vital, because now the water body is getting polluted, aquatic life is lost, and all those things. So here again, there is a different family of microorganisms, where we can call it as a combination of anaerobic microorganisms and aerobic microorganisms. Together can reduce this phosphorus in the by biological means, which means that what we say is that any anaerobic system, it will also have during the process of fermentation, produces a lot of VFA. We call this volatile fatty acids, and this volatile fatty acids are converted into energy rich products. So during the time, it will also take a lot of it will consume a lot of phosphates. So by the phosphorus accumulating organisms, and it releases the phosphate into the aerobic stream, and the aerobic stream. So again, this phosphate goes into the phosphorus accumulating organisms when it enters into the aerobic zone, because since it's already lost phosphate and a lot of energy is available, immediately it will try to multiply and form the granulation. And when this sludge is again put it back into the anaerobic system, this is again the intake of phosphate happens here. So this is how it complements. So this is the biological phosphorus. So both these things put together, the nitrification, denitrification, and phosphorus, we call this as biological nutrient removal systems. Okay. So not only on BOD and COD, now in European context, yes, already there is a BNR is quite famous, but in the Asian zone, it is not quite familiar. And now many of the plants, now we had to incorporate this BNR as well, biological nutrient removal systems, which removes the total nitrogen and phosphorus. Now, if you see the growth pattern of any microorganisms in our wastewater treatment system, so it goes through 4 phases. It's a very, very important phases. So the initial phase is what we call it as a lag phase, where when you commission from day one, we call this as a lag phase. The system, your microorganisms will get used to the pollutants. So there'll not be increase in living organisms, but whatever organisms are present, they will try to accommodate to that particular environment. So this is called the lag phase. Once the environment is quite familiar for these microorganisms, then it starts multiplying. So this is what we call it as log phase. You can see an exponential growth phase which is happening, which means there'll be a lot of growth of microorganisms multiplying. So here is the actual reduction of all your organic pollutants happens. So this is what we call it as stabilization. When we start, we say that stabilization time is 2 weeks, 3 weeks, or 2 months, so that depends upon this phase. Now, once it reaches an optimum level, we call this as a stationary phase, which means there will not be any further growth, and there will be a cell division, there will be a equivalent number of death, and which will be happening. And then you can see a declining phase where decrease in number of living cells happens, and this is what we goes out as the sludge. We call it as a sludge, so after the continuous process is done. So this is the 4 phases is very, very important, because we spend a lot of energy in this lag phase. Log phase consumes a lot of energy. Stationary phase again consumes a lot of energy to maintain this, and death phase also has, because once it is dead, it is like again a biomass. It's a sludge, what we call it as sludge. Again, we need to manage that. We need to have energy. So energy requirement is there in all these phases. So faster you stabilize, so you should go for the right process for that particular wastewater, considering the type of pollutant what is present, so that you can save on all this. We can make the process faster in some cases, and some cases we can also optimize on the energy consumption. So typically, if you take any wastewater treatment, this has to go through this scheme, where it will have a preliminary treatment. Like preliminary treatment is basically to remove the screens and grits, and then you have a primary treatment to remove all the sediments, and then you go into the aeration system, where actually the BOD, COD, everything is getting reduced. And secondary clarifier, the sludge separation happens, and again we activate the sludge back inside the process. And tertiary treatment contains the nutrient removal, biological nutrient removal, like total nitrogen and phosphate. And then a tertiary treatment can also have other polishing systems like filters. And sludge which is taken out goes into for a disposal, or converting into a useful resource, or going for a sludge digester, where we can digest the sludge. Now, this is the new norms where we have in India now. So there was a lot of debate going on, but now I think the latest notification says that you have to comply because many of the water bodies are getting polluted with a heavy amount of sewage inflow into the water bodies. So now it has been revised that you can see that the ammonical nitrogen should be less than 5 and total nitrogen should be less than 10, and COD is to the tune of about 50, and BOD up to 10 needs to be reduced. So there is no mention of phosphate, but I think for the water bodies, it is very, very critical. So we have to bring it to less than 1 milligram per liter of total phosphates. Now, if you see the energy spectrum in the wastewater treatment, the energy spectrum is like this. You can see that blue color one is for the aeration process. So 56% of the energy is consumed in the aerobic process. Very, very vital. So you have to focus on this area so that you can substantially save the energy, or we can optimize it, because certain processes require that much of energy, but we can always have the option of optimizing the energy consumption in this area. Then you have about the other pumping systems, and you can see the dewatering stage. You can see that violet color, which is about 7% of the energy is consumed in handling the sludge. How to handle the sludge, how to dispose the sludge, dewatering and disposal, again, that becomes one of the important factor. Then the pumping cost, there'll be a lot of pumpings for, so primary clarification, sludge pumping forms the rest. So the core focus should be on technologies which could reduce on the energy, because this is very, very vital, so it's not only you are going to cut down your expenses, it's you are reducing on the global warming potential, because the more the energy you consume, the more CO2 you put into the atmosphere. So any treatment solution should also focus on contributing to the environment, so not only reducing the pollutant level, it should also reduce the emission levels, direct or indirect emissions. Now, we are going into the next part of the presentation, where we are going to see about the various methodologies and technologies which can be adopted, simple solutions and simple technologies and upcoming technologies which can be effectively implemented. Okay. Now, if you see an equalization, so primarily whenever the wastewater is collected, it goes into a collection tank. It is not a simple collection tank. We call this as an equalization system, because anything what you put into the tank, it should be homogenized. So that's why we call it as equalization. So equally, because if you take an industrial scenario, the wastewater can come from different process. So each and every stream can have different types of organic loads. But what you should feed inside the wastewater treatment system, particularly to the aeration process, whatever is, it should be a steady flow. Then only you get a steady output. Otherwise, there will be a lot of variations. So you need to properly equalize the entire effluent within the tank. So normally what is being practiced is we use, there are two options, either by using a simple air agitation mechanism, so you can purge air into the system, or you can have a submersible mixture, what you see at the right, so any solutions. Now, predominantly this giving air inside the aerobic process is what generally being followed in many of the places. So only in large scale plants, people follow these submersible mixtures, because mixtures are quite costly, because always we have an air blower for aeration. So they take one tapping and put it inside. So what happens is that, see here, the equalization should be proper. If it's not going to be proper, then this homogenization will not happen. Also, there will be a lot of dead spots, which can become septic. So there should be an even movement of the wastewater, so that it gets equalized properly and then pumped into the wastewater treatment system, the first stage of wastewater treatment system. So equalization becomes a very, very vital part. It's not just a storage tank where you just leave it and put some air, do some mixing. So there is a proper design for it. So if you take a 1 MLD plant, let us say that the tank capacity for equalization is about 10 hours of storage, so 420 cubic meter. So if you are going to use an air blower, you might need around 4 kilowatt of energy to equalize this tank of this capacity. So contrary, if you can go with a submersible mixture, so that consumes only 2 kilowatt of energy. So ultimate purpose is not to aerate this effluent, is just to keep equalizing this effluent, mixing so that it becomes even. So the tank capacity, if you see, it's like you save around 50% of the energy. So it's around cutting down on the cost. Then on the types of the technological approaches for different types of biological process. Now, basically we have only two broad classifications. One is what we call it as suspended growth, and the other one is an attached growth. So when we say suspended growth, is the microorganisms remains in suspension and tries to consume the organic load by thereby reducing the BOD and COD. And when you say attached growth, the microorganisms are not in suspension, so they always try to attach to a biocarrier and try to grow on that. So these are two types of systems, and these two can be applied for both aerobic process as well as anaerobic process. There can be aerobic suspended and attached growth, and anaerobic suspended and attached growth systems. So broadly, all technologies will fall into this platform. Now, in the aeration process, mainly we use a lot of different types of diffusers are there, right from just an ordinary pipe with perforations, which can give a very coarse type of bubbles, or we can say then we can have some specific diffusers which will have slightly smaller coarse bubbles. So anything in the range of 3 to 50 mm, we call that as the coarse bubble aeration. So the coarse bubble is mainly given for mixing, not for aeration, because it has a very, very low oxygen transfer. Because smaller the bubble size, better will be the oxygen transfer. But coarse bubble diffusers are again provide a very good mixing, whereas the fine bubble diffusers may not have a very good mixing, but have a very good oxygen transfer. Now, in that they have different types. You can see again up to 3 to 5 mm size, 5 to 50 mm, and over 50 mm. So it depends on the nature of the wastewater, which type of diffusers you want to use it. And then comes your main aeration system, where people normally use the fine pore diffusers, where we have less than 3 mm size bubble size, which is used for diffusing oxygen into the systems. So these are the basic diffuser types what normally we use in case of this one. There are other systems like submersible aerators and things like that. Those are different systems. These are all what we call it as EPDM diffusers, membrane-based diffusers, or a simple pipe with perforations. Now, in an aeration process, you see that it's the control of air is very, very important, very, very vital. So you cannot put more air or less air. It has its own effect. So if you're going to put less amount of air, the microorganisms won't survive, and it dies. And if it's a very high supply, also the too much of bacterial growth will be there, and there will not be enough. A lot of microorganisms will be there, but organic load will be less. So the bacteria tries to kill among each, and they also die. So you don't have an effective microorganisms there. And there should always be a sufficient air supply. So that is so the control of air control or oxygen control in an aeration system is very, very vital to determine the process parameters. Okay, so we may say that I have sized the air blower or air compressor to the right side, but size, but it is not performing well. It could be because of the low organic loads, or excess of air being pumped in, and so a lot of factors. So the control of air is very, very essential in a wastewater treatment system. Now here comes some technological innovations, what we call it as a hydrodynamic aerators. And usually these any aerators you put in under the water. It has to meet the severe conditions, like it can have some scaling, it can have a lot of clogging issues and things like that. And the replacement frequency is pretty heavy for all these diffusers. If you're going to go for an EPDM diffusers, the EPDM diffusers needs to be replaced every year. Otherwise, you will not get the performance. So you have to remove the diffusers and put the new diffusers every year and put it inside. So the life cycle of these types of diffusers are very, very less. So there comes the hydrodynamic aerators. Uh, Before going into that, there are a few problems which would like to highlight on the conventional diffuser issues. So if you see that it is like an elastic with a small pores, so that when you blow air into these EPDM diffusers, the pore opens up and the bubbles are created, which goes up. And whenever the bubble raises, the water pressure on top of it pushes the bubbles, so there is an additional strain onto this blower. And also the sludge, because there is there is a thrust which is happening in this area, there is a negative pressure being created due to this lift. The sludge also gets into it. And in course of time, what happens is this closing and opening, it has to, like an elastic band, it has to regain its original position, but it will not happen. So at some point of time, it gets clogged or it always remains open. So that's when we say that this total diffusers needs to be replaced. And as well, what happens is that when you start with fine bubbles, slowly it will go into a medium bubble, then it becomes coarse bubble, which means from 2 mm size, it goes as high as 50 mm size. So effectively, your oxygen capacity, oxygen transfer efficiency drops down drastically. So you'll be consuming the same amount of energy, but ultimately you won't get the results because of this effect. And many of the plants, we have seen that they don't replace these things. They run for many years, even if it's not working. Even if you just go and stand on top of the aeration system, you can see at one part of the aeration will be nice. The other part, we can see like a lot of bubbles, like a bomb explosion. It will happen, which means that it has gone already. It's just, you can see a vibrant turbulence you will see in that area. So which means that the tube got punctured, and they don't replace it. If they replace it also, they replace only certain parts of it, So all these things will have an effect onto the performance of the systems. And another important problem is when the plant is running, it becomes very difficult, because we say that diffusers can be retrieved and using a mechanism and all those things. But again, placing it in the right place and having this will have a complication, because unless you drain the tank, you cannot fix it properly. These are some of the practical issues with the diffusers. And also you can see that there's a lot of clogging which happens because of any of the salt content or iron content which is present, and this will put a lot of strain onto the blowers. You can see that the resistance in this case also keeps on increasing, 200 mm water column every 10 days. So you imagine that within 10 days or 1 month, everything is gone, so we have to throw these diffusers. If you try to use this, there'll be a lot of back pressure which will affect your blower. So a lot of issues keeps coming in. Now, this is one of the innovations, what we call is hydrodynamic aerators. Predominantly, it's being produced and developed by Suzuki from Japan. It's a very, very effective aerators, which are working on a different principle. So you can see that you have a big mouth cylinder, and you can see there is a cross blades. We call it as a guide vane. And when air is purged inside, when the air is purged inside, this will create a lot of turbulence. And whatever you see on the types, we call it that as a mushroom buds. So this will create a lot of ultra fine bubbles, which means there will be a lot of micro bubbles as well as nano bubbles which are created, and a lot of turbulence. Because as I told you, any aeration system should have a proper mixing and oxygen transfer. The fine bubble diffusers has a very good oxygen transfer, but poor mixing efficiency. Okay, mixing is also very important in an aeration system. not only the oxygen transfer, the transferred oxygen has to be dissipated throughout the tank. That is ensured only by a active mixing. In this case, you have the bubbles which are produced, or very, very micro bubbles are produced. At the same time, the turbulence which is being created, which also have a very good mixing in the tank. So that is the advantage of this particular system. And also these are non-membrane based systems. There is no membranes involved. This is made out of a polymeric material. So this can be fixed on the bottom of the tank, and no sludge accumulation. Usually in a diffuser, you can see there is a lot of sludge accumulation at the bottom because that cannot be cleared. But here, because of this turbulent action, which it goes like an explosion, comes at the bottom, so it removes all the sludge, again it goes back. So always it remains in suspension. And it is also energy efficiency because it has a lot of bubbles, and the oxygen will remain in the water because of this proper mixing for a longer duration. And another important factor is your alpha factor, because when we design the plants, we consider the alpha factor, which says that it's a ratio of the amount of oxygen which is pumped in clean water with that of the actual wastewater. So if the clean water, if the alpha factor is 1, usually when we use the same parameters in the dirty wastewater, it can become half of that, 50% of that, because you cannot expect the same efficiencies. So this alpha factor is very, very critical in determining the total airflow. And if the more the airflow, then again, it has a lot of energy consumption and things like that. So this alpha factor for these type of aerators, hydrodynamic aerators, remains same as it is same for in water as well as in wastewater. So that is one of the main advantages. Whereas in case of other pumps of diffusers, it drastically drops down. So it can go as low as 0.4 as well for different types of wastewater. And the distinct advantages also, there is no pressure loss. So because in EPDM, again, you have this pressure losses. So the pressure losses can be reduced here when we compare to this aerator and diffusers, and due to which the blower head size can be reduced, due to which your power consumption gets reduced. And also a good oxygen transfer as and when you increase the height, because the one major advantage of these reactors are you can go for a deep aeration systems, so deep aeration systems so that you can reduce on your footprint. So good oxygen absorption ratio and a lower pressure loss, and longevity of this system, because need not have to, once you put this aerators in the system, you need not have to replace it for next 25 years. There are many plants which are working more than 25 years without any replacement, without any clogging. That reduces your maintenance cost drastically. And you imagine in 25 years, 25 times you would have replaced all the fine bubble diffusers. Though it is cheaper, you just calculate for 25 years, it would be almost 15 times or more than that, the investment what you would have made on this system. Now, if you see this case study also, we have just shown that how this can effectively reduce. We can also do a retrofitting with your existing treatment systems with these type of diffusers without draining the tank also is possible. So this says that, before the modification for this particular type of activated sludge process, where the BOD is 1600 and 1560 cubic meter is the flow. And the DO, you can see it's about 0.5 to 1, and it has about 190 diffusers. I mean, for the same parameters, now with 46 units of these aerators, with higher DO, this is very, very important, higher the DO, because DO always should be at least 1.5 to 2 is what you have to maintain. So we are improving the DO as well. We are reducing the energy consumption also drastically, which means you can still improvise on you can increase the flow to the wastewater treatment plant. So any retrofit where you need to go for an expansion, where you need to have additional flow, here we can retrofit with this type of hydrodynamic aerators, which are very simple to install and operate. These are the typical installation where we can see that, so it is permanently fixed, and this is completely non-corrosive systems. And There are other microbubble generators which can also be a retrofit. So whatever we are talking about is now a retrofit solution. It can be in the greenfield project as well, but can also go as a retrofit where you need to expand your wastewater treatment capacity or improve the performance of your existing systems. Now, in many cases, like any of the aeration process we have to go, it should have it should be deep. It should not be shallow, because all these oxygen transfer efficiencies, whatever is we are talking about with the conventional diffusers or any diffusers, is more the height, liquid height, better is the performance. A lot of oxygen transfer efficiencies, the oxygen transfer efficiency will be higher. So it is directly proportional. So you should have a very deep aeration systems like 5 meters, 6 meters. That will be the very ideal conditions where we get the optimum oxygen transfer efficiencies. Now, unfortunately, in many places in India, particularly if it's a sewage treatment systems, they put it underground with just 2.5 meters liquid height, 3 meters liquid height, or less than that also. There will not be any oxygen transfer. It simply will be wasting energy and money for operating the plant. But whatever you diffuse will just go into the atmosphere. It's just like blowing air into the atmosphere. There's no, not really it's getting utilized. Okay. So in such a scenario, this microbubble generators can come in handy, which can work for shallow depths also, combined along with your air blower. Or a new project can be designed in combination with the microbubble generators as well as air blowers. Now, this is the principle of, again, a venturi suction. So you already have a micro, there's a water flow. There is a narrow throat here, and there will be a high flow of water. And here you, because of the flow, a vacuum is created which sucks the air, and it creates a micro and nano bubbles. When I say micro and nano, micro bubbles is about 10 micron of size, and nano bubbles is around 200 nanometer size. So the smaller the bubbles, it will have a better affinity. One is the good oxygen transfer. The other one is this will also have our charged bubbles, so that this can attract all the particles like suspended particles or oil particles, everything, and remove it. So this can be effectively coupled along with your treatment process like this, which can be slightly outside. And your blower, so it will have two combinations of the blower and as well as the microbubble aeration arrangement. So what you see is a dispersed growth. So this is how is the arrangement. The conventional is with the blower systems. Now, where the HMB is introduced here, it will dissolve around 160%, 1.6 times, so improved oxygen dissolution happens here. Because of this microbubbles, more oxygen transfer happens. So energy saving is straight away up to 50% of energy could be saved. And if you see in the shallow depths, like if you go with the oxygen solubility with blowers, even say, let us even for 1.7 meter water depth, you can see the oxygen solubility is just 2.7. And it almost gets, doubled when you go with this combination, so about 4.5. So this is one of the distinct advantages of this microbubble addition. And another important aspect of this micro and nano bubble is this produces a dispersed growth of microorganisms. So what is this dispersed growth? Normally, in a suspended growth, you have flock formation. Normally, the flocks are getting formed, and this is how the microbial cell will be there, and there will be an flock formation. And what happens is the DO levels, even if it has this level at this point, at the flock before it reaches the microbial cell, it's getting dropped down. So not enough oxygen is getting into the microbial cell, but at the same time you need to increase this to improve this part. So that is the main problem here. But in a dispersed growth, it is that it doesn't have this flock, so directly the organic matter gets into the cell. So it remains the entire, if you see the aeration tank, you can see the dispersed growth, and you don't require again a sludge settling and all those things. So directly the water can be pumped out, and you can just have some filtration and it can be pumped. All the organic matter gets dissolved. So this is the advantage of this systems. And this is how it's a combined process, where you can see that HMB, there will be a aeration tank, tank 1 and tank 2. So this is a tank 2 where we have the circulation pump, And this HMB can be kept outside. It picks up the oxygen from the atmosphere and puts it back, producing the micro bubbles. And here we have the conventional type of air blowers also, which are purging air inside. So then further you can go for this tertiary type of treatments, and the entire sludge generation is also very, very less in this types of systems. So these are some of the innovations as far as the aeration process is concerned. Smart technologies which can reduce on your energy consumption, not only on the energy consumption, when the oxygen is utilized properly, and definitely your sludge also is going to get reduced. So sludge wasting and expenditure on sludge management also reduces drastically. Now coming to the biofilm reactors, so these are some of the reactors which are work on the attached growth principle. Now, if you see this biofilm, as I told you, the microorganisms always try to attach to a surface. It's like a dust, so it's like a glass surface. When exposed to the dust, all the dust will get settled onto the glass surface. In the same way, when the microorganisms are exposed to a surface, they tend to attach to the surface and try to grow. And it has various stages, because the attachment will not happen immediately. So whenever the microorganism comes, it will attach and detach immediately. Okay, so we call this as reversible reaction. So it takes some time to get attached to it. Then the excretions from the microorganisms will ensure that a cluster of microorganisms is formed onto the surface of this biocarrier. So that's how it builds up. And once the accumulation happens here, this comfortably sits here and tries to consume all the organics. So this is how you can see that the biofilm process. You have the biofilm here, and this is a carrier support, and you have the liquid phase, and you have this end products which are getting converted. And once this part becomes weaker and this layer becomes thicker, this will detach from the surface, and this goes as the dead cell, and which is settled as a sludge in the secondary clarifier and taken out. And fresh surface is again exposed to the fresh microorganisms to attach and grow. So the advantages, if you see in any biofilm process as compared to the suspended growth, is systems is very, very compact, because it can have a very high bacterial growth, and it can also resist shock loads because of this high bacterial growth, and effective reduction of sludge. Sludge generation will be just 50% of the conventional activated sludge process, because higher amount of MLSS is there, so lower will be the sludge production. And you need not have to recirculate the sludge, so your energy cost could be reduced, and a consistent output can be achieved because of the high bacterial biomass which is being there. Once the plant is stabilized, it can work wonders. And in the market, you find now different types of biocarriers, which are virgin plastics, virgin polymeric material, and different types of innovations have come in the market, and several things are there, mainly of polyethylene, made out of polyethylene or polypropylene. So the white color what you see is basically the virgin polymer, and the black color what you see is it's not a virgin polymer, it's a mix of recycled polymer as well. So these combinations are available in the market, and the strength, everything depends on the type of system what you adopt. So the white one always has a better life because it's a virgin one, and the rest of the ones do not have a life, because they have 80% of that is recycled polymer. So when it comes in contact, because of the fluidization nature, it comes and smashes against each other, and it can also break, and there'll be a loss of this media. Now, under this biofilm, so there is yet another great innovation which has happened, is we call this as carbon fibers. So these carbon fibers are nothing but a fine graphite crystal structure, and it's manufactured using carbonizing acrylic fibers. There's a special heat treatment process which is applied for this, and a special coating, we call it as a pan coating on top of it. And these are the strong biocarrier material which is available in the world now, which is about 7 times the strength of steel. And this is the carbon fiber which is mainly used for building aircrafts, spacecrafts, and all those things. So you imagine how strong these are. And these are like a very thin hair, and you can see if you take just one bundle of thing, it will have about 12,000 ultrafine elements of 7-micron filaments. So it's just like a hair, and it has a lot of surface area and other adhesion properties, which I will be explaining to you shortly. Now, if you see this Mira carbon will have just like a hair. You can see it can accommodate different types of microorganisms. On the outside, when it comes in contact with the water, so it can have a swaying motion and it spreads like a wing. On the outside part of it, you have all the aerobic microorganisms, nitrifying microorganisms, and the inside part you have all the anaerobic microorganisms, as well as you'll be having the denitrifying facultative type of microorganisms, and all different types of families gets accumulated in the same space. So the treatment would be very, very effective. Now, if you see that when it is immersed, because this will be like this, you can see that it gets spread, and you can see the organic load which is getting accumulated and the biofilm formation on top of this media. Now, there are several media. So if since everyone talks on a total surface area, effective surface area of the media, the effective surface area plays a very vital role in determining the quantum of media which should be applied for that particular treatment process. Now, if you see the effective surface area, normally for any biocarriers, your polymeric biocarriers, the effective growth happens inside. You can see here, inside the growth is very good. So 70 to 80% of the growth happens inside. Outside also it happens, but not that much. That's why you have some serrations at the outside, outer part of the system. That's mainly to attach all these microorganisms. If the surface is smooth, nothing gets attached. So there are two components. What we speak here is that effective surface area and total surface area. Total surface area is the total surface, inner and outer surface area put together is what's the total surface area. And effective surface area is where the microbial growth happens effectively. That's called it as effective surface area. So the effective surface area is only on 70% of the TSA. So when we design a plant, we say that so many cubic meters of, it's not the cubic meters which counts. The entire thing revolves around what is the effective surface area. And effective surface area, whatever you calculate, you can consider only on the total surface area, only 70% as which can be utilized. Accordingly, you have to size your carriers, quantum of carriers, and your aeration system. Okay, so everything will have a cascading effect onto the process. Now, when you're talking about here, there are no dead spots or, so the entire thing, the effective surface area and total surface area, both are equal, which means the entire area is being utilized by the microorganisms. Now, there is another important factor what you should consider here is the zeta potential. The zeta potential is the surface attraction of any biocarrier material. Okay, so if you see, there is a lot of it is measured using the unit called millivolt. So if you see the carbon fiber, this has about minus 10.7, and if you see the PE is 34.5, and polyacrylonitrile 24.9, polyamide 21.3. So most of the biomedia carrier what is available in the market falls in this range. It's mainly of polyethylene, and it has a zeta potential of minus 34.5. Now, how this will affect your system? Now, it's very simple. Now, the carbon fiber zeta potential is minus 10.7, negative charge, minus 34.5. Now, in the wastewater treatment systems, you have a lot of microorganisms. We call this gram-negative bacteria, gram-positive bacteria. Negative bacteria is negatively charged, positive bacteria is positively charged. Now with the positive bacteria, it's not a problem. It has an addition, but a lot of predominantly it will be gram-negative microorganisms, which are quite important here. And these gram-negative microorganisms will have a repulsion, and their zeta potential will be somewhere around 18 to 20 millivolts minus. So in which case these are very higher. So what happens? It will create a repulsion. The zeta potential on the surface of the polyethylene is higher than that of the microorganisms. So it has more strength to repel. So these microorganisms by nature will try to come and attach to the surface when it is exposed. So what happens is that it has to overcome this repulsion energy and this attraction energy. So it has to spend a lot of interaction energy to come and attach to the surface. Now in this case, it is very less. It is less than 18 or 20 millivolt of that of the, so it has a very, very negligible, repulsion force. So the microorganisms get attached to the surface very fast, immediately. So that is one of the greatest attraction of this innovation. Now, if you see the faster biofilm growth, which you cannot see in any other type of media, is that within 1 minute, the biofilm starts, building up, which never happens. And within 1 day, you can see, this is a microscopic view, you can clearly see the effects. And in 3 days, you can see the clusters being formed. Whereas in a conventional type of system, it takes about at least 2 to 3 weeks time for this type of buildup. So here what we are saying is we can accumulate more microorganisms, number one. Number two is that faster stabilization can happen here. So that is one of the important thing of this system, and it can accommodate any type of microorganisms. So one single reactor is good enough. You do not have to go for a separate tanks like for denitrification, nitrification. So all can be combined in one. Just by introducing this media, we can control BOD, COD, and your total nitrogen and ammonical nitrogen. So this is a major advantage, and to an extent, it also reduces your phosphate content. The total phosphate content can also be reduced. Now, another major issue is your the release of N2O. In many of the most of the wastewater treatment systems, you will have this emission of nitrous oxide, because this is a byproduct when the denitrification process is happening and aeration process is happening. Mostly in the nitrification process, ammonia nitrification process here. So this N2O has to be properly converted into N2. If this is not happening very effectively, it will release N2O. That happens predominantly in a conventional process where there is not much of microorganisms to, because unless there is an environment for those microorganisms to grow, it will not grow. But whereas in case of the Amira carbon, there is a very good control on this N2O, because N2O is having a higher, around 218 times the global warming potential of that of CO2. So you can also quantify and say that, how effectively you are cutting down your carbon footprint of your wastewater treatment system. You can see here the activated sludge. You can see during the conversion process of nitrification, you also have a lot of N2O emissions, which gets into the atmosphere, which has a global warming potential. Here, by default, it will not allow, because it also accumulates the denitrifying microorganisms within the matrix of the biocarrier, and only the N2 gets released into the atmosphere, thus suppressing the greenhouse gas N2O emission. And also the phosphate. So in the earlier slides, I also explained about how an anaerobic and an aerobic combination can biologically remove the phosphate. The same thing can be applied here as well, because these microorganisms have pockets where anaerobic microorganism grows, as well as aerobic pockets will be there. So because of this combination, it can effectively remove the phosphate by biological means. So one single biocarrier, which can accumulate different types of microorganisms, you can reduce your BOD, you can reduce your COD, which can reduce your ammonical nitrogen, total nitrogen, as well as phosphate. This is a combination. and one single tank is what is required, and a very effective biocarrier, which doesn't require too much of mixing like in your systems, because you also need a higher mixing in the fluidized bed bioreactors or moving bed bioreactors, because not only the oxygen transfer is important, mixing is also very important. But here, because of this nature of these fibers, the moment you put in, it will spread. So you not have to have a very turbulence inside the wastewater aeration tanks. So these are the typical arrangements, can come as a package, or these modules can be retrofitted, which comes with the supporting frames and the air grid and the biocarriers. So all put together will be the systems. And these are the savings what we'll be making, because you can see that the conventional biofilm process, you see the mixing arrangements here. You need a separate anoxic tanks, then aeration basins. Now this part can be eliminated totally, so that you cut down on your footprint, cut down on the energy of this mixing as well. So this is the advantage of going for a Mira carbon based biocarrier elements. Now, an extension of this, we can also use some of the treatment, because as I told you, two things we need to focus is, one is the energy reduction in the aeration process. Number two is energy reduction in sludge management, because we saw that 7% of the energy is consumed in sludge management, in dewatering and handling of the sludge. So any process which can, where we can reduce the energy in these two parts, which means we are cutting down on huge amount of energy expenses. So here there's another process, what we call it as multi-stage activated biological process, which works on the predator-prey relationship here. So what we have here is that we have a chambers, 12 to 15 chambers will be there, and each and every chamber we will have this biocarrier elements, and it doesn't have require a clarifier or any other treatment system. And this treatment is called sludgeless treatment systems. So what you see is, why you call this as predator-prey relationship, is that you have this primary producers. Let us say this is your BOD, which is consumed by your bacteria. So in the first stage, all the microorganisms predominantly will be bacteria with a high oxygen load, and this will consume the bacteria, the BOD and COD. Then next stage of aeration, the oxygen levels, the DO levels are higher. And here what happens is that, again, the bacteria gets consumed by the protozoans. Now the protozoans are again consumed by the metazoans in the final stage, which means there's no sludge. Whatever comes out will be only your inert matter, maybe a suspended solids, and that's it. Other than that, the organic particulates are totally converted into CO2. So this is a multi-stage process. We call it as a sludgeless treatment technology. So where you see this, the multiple stages will be there, and these are all the biocarriers. So absolutely you can eliminate on the sludge, no clarifier mechanism, no sludge recirculation. So all these are energy consuming patterns, so we can use this effectively. Okay. So this can be used for different types of industrial wastewater, as well as for the treatment of the domestic wastewater. Now, in the biofilm, there is one more new development which has happened. So everyone, you must be aware of the sequencing batch reactors. So sequencing batch reactors are the reactors where, in a sequential way, the entire treatment process happens in batches. That's why it's called sequencing. They're introducing the biofilm reactor. How the changes happen is what we are going to see. So there is a different stages of SBR has evolved. So basic one is you have one single tank, where we call that as an first stage of SBR. Then we have a cyclic activated sludge process as a second generation, then continuous flow SBRs. And so these are different forms. And now the fourth generation is what we call it as when the microbes are attached to the surface, and we introduce a biocarrier. It's called a sequential batch biofilm reactor. And it has a various advantages of high biomass concentration, high sludge retention in a very smaller space, smaller reactor, which means a reduced footprints and improved efficiencies. Now, this sequencing batch biofilm reactor with coupled along with a intelligent control system. So what is this intelligent control system is, here you need not have to operate your, in the phases, you need not have to operate the air compressors on a continuous basis. We'll have a control on the DO levels, and thereby we use only a circulating pumps. The circulating pumps and air compressor combination. So you know that you have a filling cycle, you have the aeration cycle, and you have a settling cycle and a decanting cycle. So here accordingly, we alternate between the air compressors and the circulating pump by measuring the DO levels. And that is good enough to have an energy saving of up to 50 to 56% and very good COD removal to the tune of more than 95%. So that is achievable with this sequencing batch biofilm reactors. The advantage of this sequencing batch biofilm reactors is also it is very compact, unlike an SBR system where it requires large tanks. This just requires only 1/3 of the tank what is required, size what is required for a sequential batch reactor. Now, the other stage of suspended is your hybrid membrane bioreactors. So the hybrid membrane bioreactors are predominantly combining this biocarrier with the membrane bioreactors. So membrane bioreactors thing, most of you must be aware, it's a high-end process where we use membranes in the biological process, so which can effectively filter out the microorganisms and solids which remains in the system, and only the clean water comes out. So a biological concentration of the microorganisms happens within the reactor. At one end, you get the clean water. Now, here we have different types of MBR treatment systems, which when the membranes are kept outside, and from the aeration tank, you can just pump and concentrate the sludge and put it back. You can get a very high bacterial biomass here, which can effectively reduce your footprint of the aeration process, as well as effectively reduce your organic pollutants, high amount of organic pollutants. And the other reactor is where you put it inside your submerged thing, inside your aeration tank itself. In these two configurations are available worldwide. Many of the treatment systems function, and but we need to select the right type of systems based on the application. Both has its plus and minus. Here you see the energy consumption, energy pattern is consumed in the aeration process is less, but if you see for the pumping, it's very, very high. In the same way here, we see your energy costs are very high, but the pumping costs are less. And it's quite contradicting to both. But the end quality would be very, very superior. So very good in both these systems. So wherever there is a zero liquid discharge type of systems, where you have to go for a biological process, followed by reverse osmosis, in between, you need not have to go for an ultrafiltration. You go with the MBR based biological process, so that effectively the water can be directly sent to the reverse osmosis plant, and we can carry out the zero liquid discharge process. Now, one more advancement in this system is that the only problem associated with this type of systems are the higher energy consumption and the cleaning frequencies, because the membrane gets fouled and we need to take it out and we have to go for a cleaning regime and put it back. Now, here we can have a combination of hybrid MBR, where a biofilm combined along with the system. You can see two reactors. So first reactor will be a biofilm carrier, and second one is your membranes. So what happens is that this will reduce the fouling tendency onto the membranes. So if the membrane needs cleaning every 30 days, so you can, once in 90 days, you can clean. So you increase the life of the membrane, and you don't spend energy on this and other operational expenses on cleaning, and you get a very good consistent output as well. So this is the combination you can also adapt for a hybrid MBR. And overall capex also reduces to some extent when you go with this combination combined systems. So pin flocks, yes, higher oxygen transfer and better oxygen performance, and lower fouling rates, and reduce operational expenses by combining this biofilm with the MBR. So this can be effectively utilized or retrofitted with the existing MBR treatment systems. The other forms of hybrid reactor is a combination of aerobic and anaerobic treatment systems, which can come as one single reactor for basically for sewage treatment, domestic sewage. These type of systems are very, very effective, where you see your UASB, upflow anaerobic sludge blanket reactor, coupled along with your aerobic biofilters, and all in one single tank, so you have to just pump in, and whatever sludge is being produced again is taken as an intake to the UASB. So because the anaerobic microbes can can work on this sludge. So absolutely the sludge production is very minimal in this process and lower footprint, and a combination of hybrid and anaerobic and aerobic will reduce on your energy needs as well. So this type of hybrid reactors can also be adopted for domestic sewage and for other industrial wastewater as well. So these are the technologies. Whatever we saw so far is on the different technology approaches, focusing on energy reduction and optimum performance of the system, mainly focusing on aeration and sludge management is what we saw. Now, the final part of this is your smart controls and monitoring. How a smart controls and monitoring plays a very, very vital role in reducing on the energy consumption. Now, one of the important parameters in the first slide, I said that most of the treatment systems which are designed will either sometimes it is over designed, or sometimes practically when you operate the plant, you get a lower organic load. These things you don't have a control. Let it be a sewage also. Sometimes it will be lean organic load, and sometimes it will be heavy. So but what happens is that when we put an air blower, it keeps on pumping the oxygen into the system, irrespective whether it means it's working blindly. So whatever is the thing comes, it puts the same amount of energy into the aeration system. Now, when this is controlled by a DO meter, because the main parameter which decides on the aeration performance is the dissolved oxygen sensor, DO. The DO levels what you have to maintain inside. So if you maintain that amount of DO, that is good enough. So when your organic load is higher, the DO drops down. When the organic load is lower, the DO increases. So by maintaining the optimum set point, DO set point, your blower can be adjusted. So you need just a DO sensor coupled along with a variable frequency drive, which will fine tune the blower. So you need not have to spend that much of energy. So energy saving can be as up to 15 to 20%. And in many cases, we have seen higher, this differs based on the flow patterns and organic loads, but minimum guarantee is up to 15 to 20%. You can easily have an energy saving on this. And next one is on your sludge, because whenever you go for the conventional treatment process with a recirculation of the sludge, because this is one area where we should know when we have to waste the sludge, because the more the sludge you discharge, then your sludge management costs and energy consumed in the sludge management is going to increase drastically. So you can always have an MLSS. MLSS is a measure of the mixed liquor suspended solids in the aeration tank and your TSS. So MLSS divided by your TSS gives the SRT, that is the solids retention time. So once we fix the solid retention time, the system can automatically discharge based on this set point the required amount of sludge only into the system. Because if you start wasting more sludge also, your biological system gets affected. Manual control is very, very difficult. Now, many places, mostly it is done on a manual mode. So enormous amount of sludge goes into the sludge management process, discharged out, and they're unable to maintain the biological concentration, bacterial concentration in the aeration system. So a proper SRT control with these two instruments would be very beneficial. And if you see that automated waste solids inventory management system will give a very stable operation for the plant, improved settling characteristics because your set point is fixed, and reduced energy because sludge handling energy is drastically reduced, and better quality because you retain the solids within the aeration system. So And also you have the control flexibility, because you can always set the MLSS and your SRT is our variable factors, which can always be set. So that flexibility also will be there. So you can operate the plant as per the demanding needs on the particular time frame. So this control flexibility can be done is not possible with the manual operation, particularly for large scale plants. Now, if you see why this monitoring and control, as I told you in the beginning of this presentation, this control and monitoring is very, very essential, because I should know if something is going wrong, what went wrong, that we need to know. So if you have a monitoring system, and so it becomes all the information can come to your cloud platform and to your system. Like these are the parameters normally which can be tested, like it can be a flow level in the tanks, pH, total suspended solids, BOD, COD, the total nitrogen, total phosphate, MLSS, DO, temperature, and ORP. So I just classified as monitoring. Certain things you can have an option of just monitoring and leaving it. Just you want to know how it is, what is the quality of treated water I want to see online itself, then you can have this type of monitoring systems. In some places, it becomes monitoring and control. Control means that it gives the energy optimization based on, for example, on the MLSS, on the DO levels, it can control on the, have a total control on the aeration. And ORP on your disinfection, they can have a total control on the dosage of the chemicals using this. So all these parameters can be tested, monitored, and it can be controlled from a remote location as well, just saving huge amount of energy and operational expenses. Now, the final part of this is that apart from the smart controls, we can also derive energy from a large scale sewage treatment plant. When I say about more than 50 MLD, or there's a huge amount of energy which can be produced from the biogas which is generated from the sewage treatment systems. So primarily the large scale is a activated sludge process and extended aeration process, where we have the primary settling and activated sludge treatment and secondary settling. And you have a lot of sludge which is being produced, goes into our secondary sludge also, as well as the primary sludge. Both have taken into anaerobic digestion, and which can produce energy. So by calculating this energy and mass balance, this can substantiate 50% of the energy needs required to run the sewage treatment systems. By having a proper sludge management and capturing the solids, we can generate energy through the biogas, and we can utilize that energy for running the treatment plant. So 50% is pretty huge just by capturing this. Then you imagine you put all the other controls and other things, you can still save on another 15 to 20% of energy by having a DO control and SRT control and all those things. So effectively you can hit at about 70 to 75% of overall energy needs can be controlled. And the other approach also now what we are seeing is a higher energy output from the sewage, where the sludge is again converted. Instead of a biomethanization route in the earlier one, we convert that into fuel pellets. So this fuel pellet will have a very good calorific value, which can power syngas generators. We produce syngas. Through the syngas, we can power the syngas engines, and that power can be utilized. Going with the mass balance of the, like what I mentioned in the previous slide, if you calculate on that basis, we can substantiate up to 60 to 65% of the energy required to run that particular treatment facility can be met through this, which becomes almost self-sustainable. Then you add other controls, another 20%. So 85% you can make it as self-sustainable. So these are one of the greatest advantages of for large-scale plants, because it should be, a plant should be large so that the solid productions also will be higher. So coming back to that, and the final part of this presentation is your selecting the smart solution. The smart solution, as I told you, is selecting the right process, controls, and process approach. These are very, very important. So select the right process. Let us not simply follow a technology. So we should be, our approach should be solution driven, not technology driven. So in some places, each and every technology has its plus and minus. So we need to evaluate for that particular wastewater, what type of needs are there, and analyze that, and accordingly suggest a suitable process, select the suitable process. So that is the first step in smart approach. Then monitoring parameters, so is very, very vital. So monitoring the parameters are critical, because we should know at what stage the plant is performing, or if the plant is performing well or not. So we need some monitoring parameters, at least the basic parameters, so that if there is a problem, we will be able to address it and recover it faster. This is the second approach. And the third approach is analyze and control. Not only monitor, see whether you could control these parameters and achieve the energy reduction, whatever possible. And the fourth approach is reduce annual operational expenses. The major operational expenses is not only on the energy consumption. So the energy consumption is also there, as well as manpower operation, and you don't get a proper skill to operate many of these plants. So that is again an issue. You put all the sophisticated things, and if it is not operated properly, also it's a problem. So getting the expertise for operating this, it's quite unfortunate, because in India we have sewage treatment plants being operated by anybody. You call a plumber or a watchman, anybody can come and operate the plant. So for a plumber we call a plumber, a plumbing job we call a plumber, and any electrical work we call an electrician. But for treating a sewage in a township, we call anyone can do, even a security can do. So that sort of things, what happens is that will affect the performance of the system. So we should also understand what's happening in all those things. So the remote monitoring, analyzing and monitoring will also eliminate the need of the manpower. Okay, so it can be effectively operated, or we can say it's a minimum manpower. Not that you should have person sitting there all three shifts, all those things. We just have one person there to attend to the regular issues, and rest everything can be handled. So the third approach is reducing on your operational expenses in terms of energy, in terms of labor. So this is very, very vital. And the final approach should be the focus on the technology. So technology is also the right approach. Sometimes a blend of different technologies could work. So not necessary that only this type of technology will work. So, but there could be a blend, which can be, technologies should always synergize. It should not conflict with the other technologies. So it can always have a synergy. So these are the 5 approaches what we should follow for putting up a very, very smart treatment systems, and have a very smart approach, thereby having a very sustainable treatment process in place. So thanks for listening patiently on this Sunday. And if there are any questions, I can reply. And also you can take a note of my email address, dave@kankyo.global. So if you want to have any information or any support, you can just write to us. So I'll revert back to you one-to-one as well. So thanks for listening to my presentation. So now we have a short Q&A session. If anything is there, I can reply.
Thank you so much, sir, for that very informative session on the different smart wastewater technologies which can be implemented, the microbiological aspect, and the different technologies which can be effectively implemented. Thank you so much, sir. It was a very elaborate session. The floor is now open to all the participants. You can ask your questions, post your questions in the chat box or on the Q&A panel. Or if you want to talk to sir, please do click on the raise hand option so that I can unmute you. So we have a couple of questions in the Q&A box. I will read them out, sir.
Yeah.
Okay, so it's from Asha Johnsy. For the utilization of carbon fiber in wastewater treatment, we need to have a large quantity of carbon fiber. Which method of synthesis of carbon fiber will produce the same in large quantity?
Not necessary. So the surface area is pretty uh, high here in the carbon fibers. So based on the organic loads, we decide on the organic loading rates onto that. The organic loading rates for different effluents will differ. It's not the same. So there will be a slight variation as far as the application of this organic load onto the biocarriers. So that needs to be worked out based on the nature of the wastewater. So it's not a large quantity of carbon fiber which is required, or any biofilm. The idea of going for a not only on this carbon fiber, any other biofilm carriers also. The idea is to reduce on your footprint. So obviously the biocarriers are focused on providing more surface area in a smaller volume. So that is the idea.
Okay, sir. The second question is from Noor. Biocarriers have pore in all three directions or two directions?
It doesn't have a pores. It is on the surface. It's just like a hair, so it grows on the surface of the of this fiber, and since it is like a hair, like when it is you hang your hair, there will be a lot of pockets where oxygen cannot reach. So those will become anaerobic pockets, or where the anaerobic microorganisms will be there. So the growth will be on the surface only. So there are no pores or something like that. Like any other biocarrier, wherever it is, it will only if you are going to use activated carbon filter. So this is not activated carbon. Activated carbon only will have the pores. So this is not an activated. This is only a surface which is used for growth.
Okay, so the third one, initially, how much will it cost for a small scale sewage treatment, sir, and how much area will be required?
Sewage treatments can be designed even for as small as even 25 KLD plant. So typically, if you take a 25 KLD package type of plant, it would cost less than 10 lakhs, not more than that. With these type of systems, complete system, plug and play type of systems, and so that is the cost which is incurred here, and area wise it requires very less area. So a 25 KLD plant would require roughly about 15 square meter area, not more than that.
Okay, sir, thank you for answering. And participants, any other questions? Okay, I think that's about it. What is done to remove inorganic effluents? Hello,
Yeah.
sir? Yeah.
So, see, the inorganic part of it comes mainly from pharmaceutical companies. So there, the biological systems might not work very effectively. So always remember the best efficiencies you get when the BOD COD ratios are 1:2, so or maximum 1:3, which is manageable. But if there's a lot of inorganic stuff, particularly if you take a pharmaceutical effluent where the COD will be very high and BOD is very, very low, 1:10 ratio. So which means it's fully of inorganic stuff. So the inorganic type of effluents, you have to go with an advanced oxidation process only. So biological process might not work. And based on the characteristics, it can go with an advanced oxidation followed by a biological process also. So there is no hard and fast rule, but full biological plant may not work for an if it is only inorganic. So that's why in many of the pharmaceutical industries, it's very, very difficult because it's quite inorganic in nature.
Okay, thank you, sir, for answering. I think that's about it. All the questions have been answered. We've obtained great feedback from all the participants, sir.
Yeah, so just share all the participant details, and they can also mail me if there are any further queries directly to my email address.
Yes, sir, definitely. Okay.
So thank you very much. And I think we took almost 2 hours on a Sunday.
That's okay.
So I think I shared as much as information as possible. So any specific information you want on that particular technology, always do write to me, and I'll be happy to share that information. Thank you. Thanks for joining this presentation.
Thank you, sir. Thank you for. This is for the participants. Participants, you are required to fill up the feedback link put on the chat box. Please do fill it up so that you can obtain your e-certificate.